Hello, everyone. This is our final presentation on the analysis and redesign of the staple gun. So just to recap, the staple gun is a handheld, fully mechanical tool with a production volume of 167,000 per year. Our primary customers are contractors who are using it for carpeting, upholstery, and professional projects. And our secondary customers are teachers using it for poster boards and classroom projects. In our FAST diagram, our main function is staple staples, and these are all the stub functions that we have along with that. This is our updated function component mapping matrix to show what each component in our assembly does in terms of its function. This is our updated product family design. So there are many identical functions, and the one different function that we wanted to differentiate between is ease operation. So the modules that we wanted to focus on were the handle and the load spring. This is our product family design for the handle and the load spring, showing for customer group 1, for the handle, it would be made out of steel, and for the load spring, it would be made out of steel as well. And then for the handle, for customer group 2, it would be made out of ABS, and then music wire for the load spring. These are our handle interfaces. So the handle is connected to large brackets with an outer case, and also a hook with a spring mechanism. For the load spring, there's a top cover above and a dropper right below. This is our product family assembly diagram that has been updated, and it has been built for delayed differentiation.
So designing for automated assembly, the main platform component we wanted to focus on was the dropper due to its high functional importance and high manufacturing cost depicted by our quad chart. The components directly before and after the dropper in the assembly sequence are the impact ring and staple punch, respectively. So this was our subassembly of focus to design for automated assembly. In order to improve the total assembly cost of this dropper subassembly, we used the design for automation guidelines to implement 3 design changes. The first change was to remove the notches on the staple punch, which increased the part symmetry. The second change was to add a guided slot in the dropper, which allowed for easier insertion of the staple punch. And finally, the last change was to increase the length of the impact ring from 9 millimeters to 10 millimeters, recategorizing the part from being very small to just small, which allows for easier part access throughout the assembly sequence. As a result of these design changes, we were able to modify some of the automatic handling codes and insertion codes surrounding the dropper subassembly, and it ultimately decreased the total assembly cost by $8.64.
The manual assembly analysis was performed for our primary product variant, and the total assembly time was found to be 183 seconds with an efficiency of 18%. A platform part that contributed largely to the assembly time was the brass support, and a module part that had a high assembly time was the handle. Since the handle has a high functional importance as shown in the quad chart, it is important that we redesign it for lower assembly time. The brass support has a lower functional importance, so we tried to reduce its number of parts. The handle was redesigned by adding locator pins and a snap fit for attaching it to the outer case, and the handle was combined with part of the spring mechanism to reduce the total number of parts. This reduced the handle assembly time by 6 seconds. The brass support was redesigned by reducing the 3 supports to 1. A locator for the impact ring was added, and a locator for the large bracket attachment was also added, which serves to reduce a fastener. This reduced the assembly time by about 18 seconds. All in all, these redesigned parts reduced the total assembly time by almost 40 seconds, and we have a new efficiency of 23%. However, the addition of these locators and snap fits may lead to an increase in manufacturing costs, and the thicker brass stock will likely increase our material costs.
We'll now be going into the process selection for which manufacturing process was used for both the handle and the brass support. Shown here are the key dimensions of the redesigned handle. The handle serves to detach staples and ease the operation for its user. Because of this, the most critical dimensions are on the locations of the handlebar and the snap fit. The handlebar is critical for the spring mechanism used to detach the staple, and the snap fit is crucial to hold the assembly together. The tolerances were chosen to be 0.1 millimeters. Utilizing the 7 process capabilities, we selected 2 candidate manufacturing processes and ultimately chose sheet metal working to manufacture the handle. For the process selection for the brass support, these are the key dimensions that were used. The brass support serves to ease operation of stapling for its user. Therefore, the most critical dimensions were chosen to be the locations of the locators, as they serve to hold the staple gun together. The tolerances for these were chosen to be 0.5 millimeters. Utilizing the 7 process capabilities, we selected 2 candidate manufacturing processes and ultimately die casting to manufacture the brass support.
So now diving into design for manufacturing for the handle. Before we made alterations to the handle, we first got cost estimates for the price per part. First, using the analytical method and the equation shown above, we estimated that the cost would be roughly $1.95 per part, mostly driven by the high material cost of the stainless steel. And then inserting this part into hubs and extrapolating for our volume size, we estimated that the price per part would be roughly 10.1 cents. Moving on, post DfM, we made some alterations using design for sheet metal working guidelines. As you can see, we added bend offsets to the corners to allow a sheet metal to warp as it bends. Additionally, we avoided sharp bends, ensuring that both radiuses are less than the thickness of the steel. And then finally, we got rid of sharp corners on the part, which was another guideline for sheet metal working. So as you can see, post DfM, we estimated the analytical method would be $1.89 per part, while hubs got slightly cheaper at 10 cents per part. All in all, post DfM, the handle was 6 cents cheaper.
The second part we chose to redesign was the brass support. Using the analytical method with the equation shown above, we found that prior to redesign, the total cost for the brass support was 58.5 cents per part. We then redesigned to optimize for die casting by avoiding sharp corners and adding draft angles, which then reduced the cost to 44.5 cents per part.
Moving on to our product service system, we decided to implement the concept of a rental of staple gun service to improve the customer experience and both to also reduce the environmental impact. So this would provide shared value as it would increase the value of one product between customers that would be shared. It would also be cost effective for the customers, so there would be no upfront purchase cost. You would just pay to rent the product when it's needed. So that would decrease the cost of it overall. And then it's also convenient. So it's the ability to simply rent when it's needed for occasional tasks makes it a lot more convenient for the customer experience. Moving on to reducing the environmental impact, it would provide an extended lifespan. So it encourages the reuse of one product, which would ultimately extend the product use and lifespan. It also would be more resource efficient. So it would reduce the need to manufacture and dispose of staple guns, overall reducing environmental impact. So onto our conclusions. In total, we had a 37.9 second reduction in total time. For the handle, it was a 6 second reduction, and for the brass support, it was a 17.9 second reduction. For the automated DFA, we saved $8.64 per assembly. For the DFM for the handle, we saved 6 cents per part. For the DFM for the brass support, we saved 14 cents per part. So overall, the main pro of our design is that it saves money and time, and it's a lot more accessible for both of our stakeholder groups, as it improves the ease operation for both groups. However, the biggest con that we have is that the material of the handle is still expensive, and overall, the assembly is still a lot of parts. So kind of moving on to how we would approach this project if we had to do it again, we might choose a different part than the handle to improve upon. And we might also choose a product overall with more parts to be condensed down through DFA and DFM.